think we can make a start now. Thanks for coming. I'm really glad to see so many of you here. My name is Darius and this is Yasmin. And together we help run the Effective Altruism Oxford student community. As many of you may already be aware of, Effective Altruism is the project of using evidence and reason to figure out the best ways of helping others and then taking action on that basis. And Effective Altruism has been started in Oxford essentially around 10 years ago and has since developed into a strong global community of people and organizations. And one of these organizations that will also be here tonight, and we'll hear a bit more about this later. Essentially, as Effective Altruism Oxford, we try to enable Oxford students to have a higher social impact with their lives and especially their careers. And if you are interested in learning more about this and maybe learning about how you could get involved, please just feel free to approach us after the event. And we'll also be handing around a list where you can sign up for a one-on-one with one of our committee members or for one of our upcoming workshops. Thanks.
Our speaker tonight, Dr. Sandberg, is a senior research fellow at Oxford University's Future of Humanity Institute. The Future of Humanity Institute is a multidisciplinary research center that researches important, big-picture questions about humanity and its future prospects. Sandberg's research centers on the management of low-probability, high-impact risks, estimating the capabilities of future technologies, and ethical issues surrounding human enhancement. Anders is currently writing a book on the grand futures that humanity may achieve in the long run. Tonight, Anders will be talking to us about how humanity's descendants could build a civilization with access to a full galaxy's worth of resources. I have one final announcement to make before handing it over to Anders. The Future of Humanity Institute is accepting applications for its 2019 Research Scholars Program until February the 20th. This program is a selective, salaried 2-year program for roughly 6 to 10 early career researchers who aim to address the big picture questions critical to humanity's long-term flourishing. After Dr. Sandberg's talk and before the Q&A, some people affiliated with this program will briefly outline the details for the 2019 application round. Please join me in welcoming Dr. Sandberg.
Thank you so much for this welcome. And it's real fun to be here because at this point in my book project, I'm starting to get some results. And also, I'm starting to realize I need to check this with people smarter than me. That's you. So I'm going to be outlining a little bit what I would call an argument. I'm going to try to make a good argument that if humanity survives and gets its act together, it can achieve certain things. Then we might, of course, discuss whether we want to achieve those things or what things are worth achieving. But I also want to be able to actually fairly rigorously demonstrate, at least to myself, that this is possible. So my book project is basically, it all began actually at an Effective Altruism conference here a few years ago when I had a talk title, which was something like, how big is the future? And although I'm not trained as a philosopher, sitting in the philosophy department, I immediately start thinking, how do I measure big? Of course, you can say in terms of space-time volume. You can measure it in cubic light years times years. But of course, there are other forms of bigness. We might say that somebody is big-hearted, so that somebody is truly compassionate, or that a painting has a great value. That form of bigness also matters, the bigness of value. And of course, you can discuss variety. How many paintings can we get? How many big-hearted people or post-humans or other entities can there be? And of course, what do we need to do to get there? So I'm trying to rigorously figure out things about this and write a book. So as an effective altruist project, this might not seem very effective. After all, this is a lot of astrophysics and philosophy and other stuff. There's a load of equations in the book, but hopefully we might find out things that we might want to do tomorrow to get to the next week, to the next month, to the next year, to the next century, to the next millennium and so on, to actually get to some truly grand futures. Now, humanity has so far been on a pretty amazing exponential trajectory. If you plot almost any value, like GDP, or total population, or amount of scientific truths we know, etc. They have been going up fairly exponentially for a very long time. That in itself is an interesting fact. But now we might be in a situation where things could change direction. And one obvious way it could go is, oops, it ends, we go extinct. That's presumably very bad. There are some very gloomy philosophers who actually say, no, we should be very happy if that happened. But most of us would say, yeah, right. On the other hand, others would say, yeah, actually, maybe we don't go extinct, but maybe it doesn't go that great. We end up living as hunter-gatherers in the ruins of civilization for hundreds of thousands of years. We might not be having enormously happy lives, but still, hunter-gatherers in the ruins of civilization probably have interesting stories to tell each other too. So there is going to be value in that, the world. It's just that we're missing out on a great deal. Others tend to envision the future a bit like the present. Maybe some flying cars and a bit more pollution, but basically a sane, normal, sensible world. If you think to 1950s science fiction, they're all having these roaring atomic rockets, but the social mores were very 1950s, and the society, even far in this extrapolated future, functioned like 1950s America. And I think these two possibilities are actually fairly unlikely. So I have a bigger argument together with a bunch of colleagues in a paper about possible trajectories for humanity. But basically, in order to maintain that permanent mid-level, you need to avoid existential risk constantly. Avoid also inventing anything that changes the rules for being a human. And I think that is increasingly tricky. But then again, the fourth direction, that exponential going up through the ceiling, what does that mean? And some people, again, like to say, oh yes, we get a technological singularity, we get superintelligence, and we can say nothing what comes after. We just have something religious in their gaze on that glorious whatever it is future. And I think this is a mistake too, because we can say certain things, even about a world full of incomprehensible superintelligences. They probably have to obey the law of energy conservation. They are also going to be having to deal with the laws of thermodynamics. It's very unlikely that we're totally going to change the laws of nature, even if we end up having superintelligences around. And I'm trying to see what can we say, given what we know of physics and engineering, are the limits and possibilities when something goes off there up through the skylight. How radical can it be? And maybe it turns out that we can't comprehend that, but we can make some guesses at the least at what is possible and try to see what that implies. So one way of dealing with this is what Eric Drexler, one of my colleagues at FHI, and also very much the father of nanotechnology, called exploratory engineering. We know that certain things are possible because we have already done it. And even though we might have upheavals in physics, that's not going to change the rules. Wheels work, even though maybe Aristotle is wrong about mechanics. When Isaac Newton figured out mechanics much better, that didn't change how clocks work. Einstein changed our understanding of time, but the Swiss watches were still behaving like before. Cogwheels and clocks function like they do. We might discover interesting new aspects of the world that we could use, but things that we already have actually works pretty well. And that means that that little blue corner, the things that exist, we know that's going to be around. We also have inklings that there are some areas of technology that we can't do because the laws of physics seem to forbid them. Sometimes we're wrong about that, but quite a lot of our laws of physics are fairly robust. The law of energy conservation is deep down tied to the symmetries of the universe. Maybe we're fundamentally wrong about that, but it would be a bit like being fundamentally wrong about the theorems in geometry almost. So I wouldn't exactly bet on breaking those. However, there is that white area in between where we might say, here we haven't got the technology, but we could imagine building something. We could use the rules we know from engineering, we could use the laws we have discovered, and make hypothetical constructions, analyze them rigorously, and then have a fairly confident view that this could be built. This is how Drexler looked at nanotechnology. Although he couldn't build stuff out of individual atoms, he could demonstrate that if you make a wheel out of these atoms, very solid chemical results indicate that those wheels would have certain properties. So another thing we can use is, of course, that nature, if nature is doing something, then we have a good reason to think that we can do it eventually. Might take a long while. It took us tens of thousands of years before we figured out genetic engineering. And we're still not very good at making self-replicating systems, with the exception of maybe of computer viruses. Go figure. We're not always solving the right problem. But it seems like we are pretty good at reverse engineering nature in the long run. And this talk is all about the really long run. So even if you say, oh yeah, I'm pessimistic, it's going to take us thousands of years, I'm going to say, haha, yeah, but in a million years, that's old hat. So if the nature can make intelligence and self-replicating things, I think it's pretty likely we can do it too. Also, we're pretty good at automating things, even though the first prototype of anything only works when a grad student is constantly standing there and fixing things as it's breaking, and as soon as you try to demonstrate it to your investor, it's going to totally fail. Once you got the factory, you got the standardized parts, and it's going to churn out more and more copies. And the interesting thing is, when we automate something, typically the performance goes up by orders of magnitude. It's not like it's slightly worse than humans, because then we wouldn't be doing it. Once you automate it, typically you get an enormous productivity, way more than having a lot of people doing it. And of course, once you have started automating things, you can also automate automation, which is to a large degree what's happening with our computers. We have found ways of automating handling of software, leaving that to software, and the layer after layer after layer, which unfortunately also leads to all sorts of interesting instabilities and security problems. I'm not saying that the future is going to be utopian just because we're getting more powerful technology. Rather, we're going to get more interesting problems. But the really cool thing is, this seems to imply that scale is not really a barrier. So this goes over to this point. Nikolai Kardashev, a Russian astronomer and very interested in the search for extraterrestrial intelligence, in one of his classic papers, he pointed out that actually the scales of activity of a civilization seem to be restricted by the laws of nature. But that doesn't mean that they have to be just in a country or on a planet, because it's possible to scale things up and move on a larger and larger scales. This is interesting if you want to look for civilizations in the universe, because if you assume that all civilizations are a bit like Earth, and there's going to be a bunch of underfunded alien astronomers with a radio telescope, you're going to be looking for a particular thing. But that might be rather erroneous, because actually there might be much bigger civilizations that are much easier to see over very long distances. Not because they're trying to send a message to us, but just we're noticing their industrial activities or their advertisements or whatever they're up to. So he's making this very bold claim here that maybe there is no intrinsic limitation of the scale. So basically this talk is going to be a little bit of testing. Can we see if we can scale things up all the way? So first things first, just a brief detour. What would actually a good future be like? So when we think about utopia, we all have our cultural baggage of ideas about what is good. And I'm just going to briefly run through some of the possibilities that seem possible to get to. So not all of this is going to fit into the talk, but I was kind of trying to hint at what I'm dealing with in the book. It seems like actually we're currently having a fair bit of crisis about material poverty and ecological unsustainability, but the laws of physics actually doesn't seem to indicate that we have to live as hunter-gatherers. Actually, it seems like you can have sustainable societies with at least current American standards of living essentially going on indefinitely. And of course, my old research has been about whether we can also improve ourselves, both in terms of being healthier and living longer, or being happier and smarter, and maybe even more moral. And then, of course, the topic of this talk is going to be about actually going out there to space. Even though it's actually quite fun, I could do another talk which was just about how to survive on Earth for the next billion years, and do life extension for the biosphere, so it lasts for at least 1 billion or 2 years more. And then, of course, surviving for a really long time. So most mammalian species hang around for about 1 million years or so. We have been around for about 200,000 years, so we at least got 800,000 years to go if we do statistics badly. But that's kind of implausible because we're not a normal mammalian species. We're spread out across the world very widely, and actually we are very adaptable. We exist in a lot of weird ecological niches that we have invented ourselves. So it might be that we could actually survive as long as the biosphere is around, assuming we can avoid a mass extinction event, which if we need to be have a certain technological ability and maybe some agility to dodge. 1 billion years is a ridiculously long time. But were we to actually set up a solar system, then we can last as long as the solar system, which is about 5 billion years before it's starting getting messy. And of course, if we just start setting other stars, well, stars are going to be shining for literally trillions of years. Barnard's star, which is sweeping past us right now a few light years away, that's going to be shining still dimly in 1 trillion years. Were somebody just to build a habitat around it, well, that's going to get a bit red sunlight for 1 trillion years at least. And of course, if you use artificial energy sources, as far as I reckon, it looks like we could survive to at least 10 to the 33 years in the future, when protons start decaying and we're getting into trouble because we're running out of matter. I will also be talking a little bit about that we could, of course, get all the energy from the stars and actually move things on a ridiculously large scale, like moving galaxies. Turns out that if we really want to, we can make the Milky Way move about 50 kilometers per second in any direction we choose. Might be good because Andromeda is coming right at us, but we'll see what we actually want to do. And of course, for computer nerds like me, it looks like it's totally feasible to do at least a Google computations over the future. And probably much, 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 much more, which could be used for some interesting computations or at least an awful lot of Facebook and computer games. And, well, this is too much text anyway. Then there is, of course, what goods we might want to be aiming for. And it might be just survival. It might be happiness. It might be creating ecosystems. There are also people who think, oh, well, moving galaxies, that's not my cup of tea. I just want to have a little village in the Cotswolds drinking tea and with the vicar, please. So there is an interesting dialogue here between the very grand futures which involve moving galaxies around and the people who actually think, no, there is value that exists and we shouldn't exchange that for fictional or future or weird values. So there is a very interesting dialogue to have there with the people who want modest rather than grand futures, have conservative values rather than maximizing values. There are also interesting possibilities about, well, how much can we abolish suffering? Right now, I have a brain that can not just make me suffer because I hurt myself, but if you just start looking very bored, I will hurt inside because I'm feeling social exclusion. A part of my mind, instead of reacting in the right way, which is of course telling more jokes and being more social, instead just makes me feel bad. That should be fixed. Yeah, exactly. We should fix that. Now, some of you might know Dave Pierce, who's been working a rather long time on maximizing happiness and of course abolishing suffering, because there's an awful lot of it out there. And if we could fix suffering, which is both an interesting neurological and philosophical question whether that's possible, if that works in humans, maybe we also have an obligation to do that to the animals. And maybe then go out in space and trying to find suffering aliens too and help them. So there's some very interesting questions here about where the limits are there. And of course, we might also want to spend the future on thinking deep thoughts or creating great art or just doing unexpected things and making the universe a bit more creative. Not just a steady progression of gravity and entropy moving things along in their orbits, but actually adding a bit of art and whimsy to it. That's just some of the possible goods, and you can probably come up with better lists. Now, starting out here, what about actually achieving a post-scarcity? So when it comes to energy, we can make an argument that right now we're having an energy problem, and moving to a world that is actually using 100% renewable energy is by no means trivial. It's a really tough problem. It's a tough problem because we want to change an existing, very complicated economic and energy order. But from a physics standpoint, it's no problem at all. There's so much sunlight. And even our currently relatively crappy solar panels actually have more than enough energy. So if you calculate the amount of power modern Western human uses and then turn that into solar panels, you realize that, well, it's basically the amount of solar panel down here on the floor that in the good desert sunlight would be powering all my extravagant lights. You can have your own 26 square meters. Yeah, we need extra because unfortunately it's sometimes cloudy and some of us live in Sweden or Britain where there is not that much sun and there is that thing with night. So you need more solar panels. We might want to make them more effective. But really, physically it's actually not that hard to do this. Then of course, I'm part of a post-carbon transition project trying to figure out how to get there. That's going to be tricky. But the laws of physics definitely do allow us energy post-scarcity. And the cool thing is, once you have enough energy, you can actually do an astonishing amount of other stuff. Because basically, the reason garbage is that it's hard to sort out into the elements and put the elements back into something that you care about. If you think about the plastic in this cup, well, that carbon and that hydrogen could be rearranged into a lot of other forms. 3D printers are an obvious first demonstration. We can recycle plastic a fair bit. Eric Drexler's work on atomic precise manufacture really shows that, yep, the laws of physics definitely allow us to recycle matter as long as we have enough energy and dump the waste heat somewhere. That's an important thing. It's always going to be a matter of energy in and entropy out. And you don't want to add too much entropy because then you overheat the environment, no matter what you do with climate change. The interesting thing is 1 kilogram of organic stuff, like the furniture in this room, is about 20 megajoules per kilo. In principle, you could take it apart, literally atom by atom. It will cost you about 20 megajoule, and then you put it back in and you get you have to pay or get the energy difference. Currently, we don't have very good methods of doing that. So they tend to be highly entropic, and they tend to lead to an awful lot of waste heat, which is why so much of our manufacturing really sucks. If you do this with a lot of precision, you can get closer, for example, to biology, which is doing this very much along gentler paths. You don't produce that much entropy. It might be a little bit slower, but that is something we can actually optimize away. And it seems like actually the laws of physics allow us to do this at a surprisingly good rate. Basically, making a matter compiler that assembles things has a productivity of about a kilogram within about 20 minutes seems totally doable as long as you have energy. It's going to be a while before we get to APM because nanotechnology got sidetracked because of various sociological reasons, but it actually looks like it's getting back on track. And that's going to be important because it actually looks like it's pretty likely that we are going to get a fairly post-scarcity society eventually. And then, of course, the interesting problem here is making this transition well. That's for a completely different book and a completely different talk. But it seems like actually we have potentially a pretty good future. Another interesting topic for maybe another time is discussing how to think about a future that is post-scarcity and is not necessarily that competitive. Because we have evolved in a situation of scarcity. We tend to think that, oh, if I can't get that, somebody else will, so I better grab that even if I can't use it. We have basically evolved to have a hypothalamus telling us to eat as much as possible because starvation might be around the corner, which of course means that since it's easy for me to eat, I'm getting overweight. We have changed our circumstances, but we still might need to change our brains. And that is just about eating. We might have similar issues about competition in a post-scarcity society. I should probably hurry up, but yeah, a lot of the stuff we are working at FHI has to do with questions about artificial intelligence. And again, it doesn't seem to be any reason why it should stop just below human intelligence. So a world where you get the intelligence on tap, you end up with an awful lot of intelligence. Not necessarily super smart, because for many tasks you don't want a super intelligent lawnmower, you just want one that doesn't take your flowers. But maybe you want to have a lawnmower you can discuss philosophy with, and in that case we might very well get it. The little problem here is, of course, that we might need to actually make it safe, which is not a small problem at all and worth, again, an entire lecture. Okay, But generally, when it comes to food, people have been arguing since about the 1600s how many people can actually live on Earth. So Leeuwenhoek, the guy with the microscope, he estimated that if everybody had farming as efficient as modern 1640s Dutch farming, we could have about 13 billion people on Earth. Which is not terribly far off from a lot of other guesses. A lot of people have been trying to guess this based on various farming practices. Some people think that no, that's unsustainable, so Paul Ehrlich think that now at most you can have 1.7 billion people. If you say that actually we can do much better with modern agriculture, 10 billion seems to be doable. If you say screw nature, we're just going to pave it over with soybeans and the oceans are going to be lovely algal farms and yeast farms, then you can definitely have several trillion people. Again, is that a good future? Well, it depends on whether you love having a lot of people around. If you don't care too much about food but think people are the best thing, this is a really good future. If you think that, no, pristine nature is a good future, then you probably want to have much fewer people. But this is a kind of choice, and it's partially technology dependent, how much agriculture can you do, and partially just a choice about what values you have. So I've been nerding out myself for the book about hydroponics, which is awesome, because the basic argument many people mentally do is, okay, we need to have agriculture to survive, oh, that's going to deplete the soil. We have removed, I think it's about 133 teragrams, or maybe it was petagrams of carbon from the soils of the world over the past 300 years, which is kind of, oops, not good. So you might imagine that, oh, if we want to stay around, we're going to still deplete the soils. But you can, of course, do soil-less agriculture. You use nutrients that you pump past the plants, and that way you don't deplete the soils and you don't take up that much space out of the ecosystem. You can, of course, also add extra carbon dioxide to the atmosphere in the greenhouse, and you add the LEDs, hence that horrible pink color. That is really optimal for growing, and actually you can keep the lights on even during the night. In fact, you can put that greenhouse down in an old subway or a mine, which means that no pests are getting in, and you can totally control the environment. So this seems to be able to generate food without any contact with the outside world, as long as you have electricity to those LEDs. So this is fairly energy intensive. Normal agriculture only uses energy for the tractors and tools to harvest and tend to the crops. This might actually be given the sunlight, but it can recycle water, and it doesn't use the soil. Normally, to get the nutrients, you actually mine minerals. But I've been looking a little bit in, can you actually use sewage? So basically, we have a closed system where the food is getting eaten by humans, they go to the loo, and then the product of the loo, you actually put it back. There have been various interesting research on that. We're not quite there yet, but there is quite a lot of projects that are almost close to the process. You need to balance various things. There are some nutrients that actually do tend to deplete, so you need to maintain that. You want to make sure that you don't build up certain toxins or the heavy metals, but it actually looks pretty doable. Of course, for space, people have been really interested in doing this. And it turns out that we need about 20 to 25 square meters of hydroponics. So I did a bit of calculation and found that, well, if we put solar cells that are pretty inefficient, this is kind of average use across the year of 50 watts per square meter on top of our urban areas, then we use that to run hydroponic farms as effective as a particular lettuce farm in Tucson. Then we can feed 44 billion people. I would love to have somebody who's interested in hydroponics and agriculture help me do the calculations a bit more carefully, but it definitely looks like you could actually make this kind of closed system that's totally sustainable, can go on as long as you have sunlight. That's kind of good news for the ecosphere. We might, of course, want to figure out how to get there, but I'm very happy to show that actually there is a there we could try to get to. Now, space. Well, the interesting thing is getting people to think about hydroponics. If I say I want to do hydroponics to help people in arid areas or that have food scarcity, people will say, that's nice. If I say, oh, I want greenhouses to function in space, a lot of people get very excited. So actually space might be useful to motivate doing these things that is actually quite useful down here on Earth too. And yeah, by the way, I have forgotten about the cattle, but we have experts here of in vitro meat, so I think that's the solution there. But thinking about what we have already done in space, I already mentioned the closed ecosystems. And we already have demonstrated that you can keep people for years up in at least Earth orbit. Can we use this to make an argument that you can actually settle space and do it in grand style? A lot of you have probably seen this picture by Bonestone and others that are based on the work of Gerald O'Neill in the 70s. So he led a NASA program to study the possibility of really settling space and industrializing it. Basically, the idea was the most profitable thing to do in space was build orbiting solar panels that were beaming down energy. You would be mining the moon for material to build these solar panels. To live in, you would have these gigantic rotating cylinders to live in. And they made a lot of beautiful pictures, and they become kind of almost cliche in science fiction. And this is just something of how the future in space is going to look like. Now, this is a very nice future, but getting there might be tricky. So my argument is something like, okay, can we demonstrate that it's actually possible to do an initial threshold of effort, and then you have something that's stable and grows. Now, most people who really like space will say, oh, we're going to go there soon, or we're going to make lots of money from platinum in asteroids. Typically, kind of, asteroids contain a lot of platinum, mining, question mark, lots of profit. Space mining is really tough because it's not just that you need to get stuff up into space, which is expensive, but once you have stuff in space, getting it down is almost as expensive and hard too. Similarly, thinking that space could have an enormous growth rate, maybe in the long run, but I'm not going to try to do that. And of course, if we had anti-gravity or a nanotechnology that could make an orbital elevator, it would be much easier. But I'm trying to make a minimum viable product thing. So instead of thinking about these wonderful Stanford Tauruses with the interiors that are looking like California, it's going to be more like this, which is the International Space Station on a bad day. And I think one can make a pretty good argument that we're almost there. So if you think about the preconditions of actually making a space settlement, well, we need to get up out of Earth. We know we can do that. We need methods of transporting things around, and at least in the vicinity of Earth we got that. If you can actually make closed ecosystems that can last for years and people can survive in them for years, you can send them to other parts of the solar system. When it comes to life support, well, again, we have done most of it. So if I'm putting little green check marks at the things I'm pretty confident we already know how to do, there are some parentheses and some question marks. We haven't demonstrated yet the total recycling in space. We have various ground-based ecosystems. Radiation tolerance, we have somewhat good, but we need to improve that. Gravity, I think, is embarrassing. Tsiolkovsky, the guy who came up with the rocket equation, the space settlement in the first place, he was already talking about how to make artificial gravity by rotating things. We know how to do it. It's just that he had this idea of a wheel-shaped space station. And a lot of people assume that that's how you must do it. But that's going to be an enormous amount of material. That's hard to build. So it has not been built. But you actually can just use counterweights. So if I have my habitat here, I have a cable, I have a counterweight, I rotate it. Now I can get pseudo-gravity. This is probably relevant because of biology. So if you look at astronauts when they come back from space, they actually have a lot of interesting ailments and things. And a lot of that is probably because we're not very good at surviving in microgravity for a long time. In particular, and this is kind of relevant, is that it's not entirely clear that reproduction works very well in space. Not just that the zero G sex is a problem, although many people have given far too much thought about that question. But it might actually be that actually early development might need gravity. At least some plants get very confused when they're growing from seedlings in zero gravity. So it might be that we actually need a little bit of gravity to actually be able to have the next generation in space. There might be other biological things that need to be fixed. So here are some of the question marks. When it comes to energy, we have solar panels, we actually know that. The materials, we know roughly what materials is out there. I'm going to get to that in a moment. And I think one can actually manufacture. But that has not yet been demonstrated. Actually, going to an asteroid, scraping off some material and doing something interesting with it, that's something that still needs to be done. But it can probably be done within the next few decades. It's not terribly, terribly far, hand-wavingly far away. It's actually doable. I think we actually think we can do the biospheres. It's just that we need to do them much better because we have not yet pushed that very much. Interesting questions about long-term risk management. I think it's going to be risky. But basically, I think the image I'm getting in my argument in the book is that imagine something like the International Space Station. And you have a kind of tank of algae and yeast producing nutrient sludge. And you live there and you eat your nutrient sludge and it's getting recycled and you have some greenhouses and other ways of getting oxygen. And occasionally you go to an asteroid, you mine some material, you turn that into more space station, more manufacturing for nutrient sludge, and eventually your kids move into the new space station. This is not terribly appealing. This is not the barbecue on the patio on the O'Neill cylinder. This is very much like a very cramped, claustrophobic lifestyle. Yet, a lot of people actually have cramped, claustrophobic lifestyles. And a fair number of them are even adapted to it and think this is normal. That's the tragedy and beauty of the human condition. We can adapt to almost anything and convince ourselves that this is totally normal. It's a good thing that there are some people who actually don't like normal and may change that. But it seems very likely that we could actually do this kind of most primitive possible, minimum viable product space settlement. And if that works well enough, if the risks from the solar storms and meteors, etc., are low enough, and on average each space habitat produces 2 more, even at a very low growth rate, well, before long you have turned the entire solar system into copies of the International Space Station. That's kind of an astounding thought. This is not necessarily a great future in the sense that people living in these cramped stations are living the best possible life. But this looks like it's definitely physically possible. So then, of course, we might want to aim for the deluxe space stations. So Mars is, of course, super popular because it's a classic idea and it's a place, unlike asteroids just hanging out in space. The problem there is not so much rockets, sorry Elon. The rocket part is kind of solved. Well, there's some technical hurdles, but basically we know how to send stuff. One big problem, however, is the gremlin. A lot of the missions to Mars have failed in the past because of the Martian gremlin, as people joke. But it's actually hard to make things that are robust enough to survive a few years in space when we get there. So you actually want to have a lot of robustness of your technology. And then, of course, once you get to Mars, you want to build a self-supporting habitat. And I think it's also the wrong move to go down a gravity well, but that's my taste. I prefer asteroids and moons of Saturn. One of the interesting things a friend and me started working on was, could we actually come up with could we make everything we needed on Mars? You probably can't read this diagram, but this is kind of a sketch for the core of industrial metabolism of a Mars industry. So over here you got the atmosphere with nitrogen and carbon dioxide, and over here you got various substances you find in typical Martian soil, like titanium dioxide, magnesium oxide, nickel oxide, there's iron and iron oxide, aluminium oxide, quartz, of course, and some sulfates, some calcium carbonate, some salt, and most important, a bit of water. Now, what can you do using that? Well, it turns out that if you take the carbon dioxide, you take the water, and you split the water into hydrogen and oxygen. When you mix the hydrogen with the carbon dioxide, you can make syngas, which is a rather noxious mixture of hydrogen and carbon monoxide. If you lead that just over iron oxide and heat it, you get iron. You can use syngas, this stuff, also to make a lot of other useful metals. That's nice. But you can also use it to make methanol. And you can also make methane out of carbon dioxide. And that way you can make acetylene and ethylene and propylene and formaldehyde and a bit of benzene and now you got a good start of your organic chemistry department. In fact, now you can start thinking about plastics. You can essentially do the organic chemistry. Well, another interesting thing is, of course, the components to make cement, not too hard. But also, more importantly, you can make silicon, which is very nice for making solar panels, because you need some way of powering all this, because this takes energy. And the really nice news is the amount of energy it takes to make a solar panel is less than what you can expect to get out of that solar panel. So you would get an exponential growth if you automated this. So this seems to be a pretty good way of making an argument that yes, you could definitely settle Mars this way. I'm trying to do the same thing with typical asteroid material, and I get roughly the same result. They're slightly more awkward because not everything is in there. And of course, when you start thinking about the universe and how much stuff there is out there, the asteroid belt is huge. It's still a small mass compared to Earth. But if you compare that to the crust, the stuff that we are actually toying around with as the biosphere, it's actually much more. So we have about 10 to the 12 kilogram of crust that the life is touching. But we can touch 10 to the 21 kilograms of asteroid material. That's a lot more. There's probably limits on how much we can do, because we as living beings, we really want a lot of nitrogen, and the asteroid belt lacks nitrogen. Fortunately, Titan has an atmosphere of nitrogen. We can probably come up with some deal and import a little bit there. But if you do the calculations, it seems like, yeah, turning this into habitats for 1 trillion people, yep, that's well within the margins of errors. You can probably do way more than this. That's a ridiculously large ecological habitat compared to Earth's surface. Even if we do this just because we like plants and animals and not so much care about humans, we just want to have gardens orbiting around, that's going to expand the Earth's surface a lot. If we want a lot of people, that's also possible. And you can have a lot of very different habitats and very different cultures, because there is so much space. And if you don't like the neighbors, just push off a little bit and soon you're very far away. Of course, we can also start thinking about automating this process. We get energy, we mine stuff, we get it into orbit, we make solar collectors, and that gives us energy. And that kind of exponential growth, it turns out when you do the math, you can disassemble Mercury in about 40 years. And that's really good, because then you can build Dyson spheres, which are my favorite toy. I want one. I want one so much. So, as you might recall, Freeman Dyson is an awesome physicist, and in the 60s, he also pointed out that maybe we should be looking for weird infrared sources in space, because given the energy usage our civilization is doing, it looks like within a few hundred years we're going to need to use all the energy the sun is outputting. Which most normal people say, yeah, that's kind of reductio ad absurdum, something has to break. And his view was, well, why not build solar collectors orbiting the sun? And then the next step is, of course, to observe that civilization might very well do that. That's kind of natural endpoint of colonizing your solar system. All the energy the sun is outputting is, of course, going to be re-radiated eventually as waste heat. So you should look for a weird infrared source, and people have been doing that since. So Dyson and Kardashev very much are in the same wavelength here of look for the industrial waste of advanced civilizations. So what would you use a Dyson sphere for? Well, first you get a ridiculous amount of energy, 10 to the 26 watts of power. I want to run a lot of computers on that. But of course, this could also be habitats. You can't really build a solid shell, but you can certainly make a lot of orbiting things. And of course, if you put sensors on the outside, you have a structure that's 2 astronomical units across. That's a darn good telescope. You can literally read alien newspapers of thousands of light years away. You can use this to map out the universe to a ridiculous degree. In fact, the biggest problem might be that the resolution is so high that the time to scan the entire sky at it is actually longer than the lifespan of the sun. So there are some other problems. You actually need to decide where to point it. You can, of course, use it also as antennas. Again, if you have a very big antenna, you can focus signals over very long distances. That also means that you get a pretty nifty weapon if you have some neighbors you really, really don't like. Because you got 10 to the 26 watts of power, and you could have a phased array 2 astronomical units away, which is pretty good for boiling off planets. However, the heroes in the spaceship dodging around in that solar system, you can't hit them because you can't see them because they're light years away. So a few years later, you know where you should have been shooting at them. So there are actually some very interesting limits on how you can weaponize Dyson spheres. It's not even clear that if you have two Dyson spheres shooting at each other, that they could harm each other permanently, which for me feels like it's some kind of message of peace. You can even direct the solar output in a particular direction and use this to move a star. Very slowly. It's one of the wussiest rockets ever imagined. But it turns out that if you do this, after a few million years, you can do a close pass to another star and do a gravity assist, and now you're moving tens of kilometers per second. And if you keep on doing this on a galactic scale, you can literally move galaxies. We can't actually get enough speed this way to move galaxies out of gravity well of the local groups. We can certainly use this to throw stars. So if we think that we want to move our stars from Milky Way to the Virgo cluster because it's way cooler over there, we could. Whether that's a smart idea, I'm leaving for our descendants to decide, but this is doable. At this point, of course, you might say, wait a minute, what's going on here? How did we so rapidly go from thinking about using sewage to grow plants to moving galaxies? And the trick here is, of course, that we're living beings. Living beings have this tendency of taking nutrients in the environment, using that to lower our own entropy. We're all Maxwell's demons. We're kind of fudging the laws of thermodynamics by taking useful low entropy stuff, turning it into waste heat, and lowering the disorder of ourselves. And since we're also living beings with nervous systems, reducing the uncertainty of the future. We're making investigations to figure out what to do, and then we do actions that hopefully lead to desired outcomes. This produces very weird things because we might desire things that are totally on the contrary to entropy. We might actually turn around entropy. Entropy, of course, always wins in the long run because we have to actually use nutrients and stars, etc. So there is a lot of waste heat eventually. But we can certainly set the stars in motion. We can reorganize planets. And we can actually kind of win in the areas we care about. And this seems to be a recurring thing because we actually have this power. And because we can reproduce or make robots that can reproduce, we can scale things up to enormous scales. And that is why we can mess up galaxies. Okay, I'm probably totally running out of time, but okay. So how do we get to other stars then? Well, the cool thing is we could have done that already in the 1970s. The Voyager probes were not aimed at anywhere in particular on the sky. They were intended to visit the outer planets, and they did a marvelous job at that. And now we're going to keep on sailing for a very long time. But if we had nudged them a little bit, they would have been able to go to another solar system. They would, of course, just be an inert lump of metal with some interesting artworks on. But we could send things in the 70s to other stars. Making something that is functional when it arrives, that's a bit trickier. But it's not terribly impossible to actually send things to the stars. People in the 70s were working on interesting things like the British Interplanetary Society's Daedalus project, which was a very carefully thought out interstellar probe. Again, a beautiful example of exploratory engineering. It was intended to be fusion power propelled. It's beautiful, and it's still kind of state of art in a detailed scale. It's also feeling very unwieldy, because the fundamental problem is the worst equation in all of physics, the rocket equation. Basically, a rocket needs to move not just the payload that you actually care about, but also all the fuel that it's later going to use. So it needs to move that heavy fuel, and for that you need even more fuel, and that means that it needs to have a ridiculous amount of fuel tanks. This is very sad. You can try to fix it by having very high exhaust velocity, which is harder to do, but still the rocket equation requires an exponential amount of fuel. So you want to get around that. Even something using fusion and being very futuristic has these limits. But you can use an external launcher. What if you instead used a very big laser and showed it, let's say, on a solar sail, or in this case, just a reflective sail? The sail doesn't need to carry any fuel. All the fuel is sitting down there on Earth, in this case, probably a hydroelectric dam powering the laser. And that way, you could actually make things that are likely to be able to reach ridiculous velocity, at least if you make it very small. So this is the breakthrough Starshot chip, very intended to essentially use this to launch small chips with solar cells, 20% of light speed towards, I think it's Proxima Centauri right now, but they're open for a lot of other targets too. And the awesome thing is they're hoping to do this within maybe 20 years. It's serious funding and they're actually doing serious engineering on it. The trick here is you don't have a lot of fuel you need to scatter out. Of course, those ones are going to have a hard time slowing down. But anyway, that is probably the trick to get to the stars. Now, instead of using that kind of rocket, you want to accelerate it. Then there is a lot of problems, and I definitely don't have time to get into this, but basically there are some speed limits. The most ultimate one is, of course, the light speed limit. The one that is really annoying is probably colliding with dust. So this is velocity, and this is the size of a probe. Basically, you want a fairly big one so it can survive a dust collision, but then you need way more energy. So there is an energy limit you have. There are also problems of heating and all sorts of other very fun stuff to work out the details of, and I'm totally not going to be dealing with that right now. I'm just going to be saying that there is a lot of fun stuff here. And also, those of you who happen to be astronomers, please, please, please come up with better ways of estimating the density of gravel in interstellar space. We have no clue. The thing is, that you might have noticed those beautiful dust lanes in that first picture I had of the Milky Way. The fine dust blocks light rather well, so we know basically between us and the galactic center there is at any point in time at least one little dust particle that captures the light. But that's the fine dust, and we can build a spacecraft that can survive plowing into that even if it's moving fast. It's the gravel that's the problem, and gravel is rare and it's going to be transparent, so we need other ways of measuring that. Okay, anyway, now one interesting thing that happens when you start thinking about this is that some people are suggesting we should make multi-generational spacecraft. The problem is they need to be really big because you need to have at least a little city of people living there. And if they're going to arrive there, wherever there is, in less than 100 generations, they actually need to move at a fairly brisk clip anyway. So basically, it doesn't seem like you win very much from that. And the faster the craft needs to be, the smaller you want it. You probably wanted to make it javelin-shaped if dust is a major problem. And you're probably not going to put an engine in it. You want to launch it using, for example, your local Dyson sphere. That's how I did it in my paper. You just use very big coil guns to accelerate it using essentially an afternoon of sunlight to send off all the craft. And then once it arrives at the destination, half of it drops off and it projects a laser back at a shield and slows it down. And this, of course, means that that kind of square-jawed hero from classic pulp science fiction doesn't seem to be very likely to be the person to get to another star system. It's probably much more like, you can't really see it, a little microchip with nanotechnology on it. So if I'm going to make a bet, I would bet that actually no organic human is ever going to go to another star, unless there is some ridiculous super civilization trying to prove something silly. We humans, in an organic form, can probably definitely settle the solar system. But I think it's pretty likely that nobody is ever going to go organically to another star. We might then send robots maybe to grow humans in a biological form, or we might upload ourselves, or we might say that, okay, actually it's our AI descendants that are so much better at everything, they get to keep the universe. But it's probably not going to be that hero with his nuclear rocket. Then the question is, how far do we need to travel? And it turns out that if you have a fixed travel distance, as you increase that, eventually all the possible destinations form a network. So even if you can't go from there to there straight, you might actually do it in several hops. So this is percolation theory, in continent percolation to be exact, and it turns out that the answer is about 8 light years. If you have a craft that can travel 8 light years, build a colony somewhere, and then send off new craft, now you can take the entire Milky Way. So that's basically what you need to be able to do. If you can hop 8 light years and build new colonies. And notice that the earlier discussion about settling the solar system, that was basically what's needed to build a colony. So by the point you can do this, you actually got the galaxy. As a bonus, of course, besides getting all of this, all 300 billion stars and all the things around them, including a very lovely supermassive black hole in the center that you can extract so much energy from. There is, of course, the rest of the universe, expanding at a brisk clip. In fact, we might want to go there before it disappears over our horizon. And again, you can calculate how much you can reach if you travel at different speeds. And now you really want to go fast. Turns out that if you actually travel close to 99% of light speed, which is probably easier in intergalactic space because it's cleaner than galactic space, you can reach about 4.8 billion galaxies. That's a lot. Basically, you automate stuff, build your Dyson spheres, you send off your probes, they arrive at some remote galaxy on a little asteroid, and then build a Dyson sphere, and now all the stars are getting settled. This is interesting because what's happening here, of course, depends on the values of whoever sent off that. So if their goal was, okay, let's put our flag on everything, or let's make parking lots, or let's produce happy children, or whatever it is, that value will now be imprinted on a literally 5 gigaparsec radius volume. This is about as big as life can make anything. And that's actually larger in scale than anything we normally get in cosmology. Because the galactic voids and filaments are actually just on a 200 megaparsec scale. It looks like physics allows life to create larger structures than we normally get in cosmology. So that's the visible universe, and this is the part we can reach. The cool thing is there are parts that we will still not be able to reach. We can see galaxies that we will never ever touch. If we get a message from aliens over there, well, c'est la vie, we will not be able to send a greeting back to them. We will never reach them. And so the cool thing is Kardashev has his famous scale where he measured the power of civilization, literally in the energy output or how much energy used. So he talked about the level 1 civilization, one that uses all the energy on the planet. And we're not there yet. We're at 1/10,000th of that. But then you have a solar system civilization that literally is 1 billion times more powerful. And then he talked about the galactic civilization, which is about 100 billion times more powerful. And of course, these ones, if they exist, would be pretty noticeable. So there have been some surveys that I looked after, and we haven't found one yet. So they probably don't exist in the near parts of the universe. This, what I just described, however, was an intergalactic civilization. So that would be 10 to the 46 watts of power. And that's just the starlight. In fact, the amount of the mass of the starlight that right now is in a transfer between the stars is actually larger than the mass of the planets in a galaxy. So, starlight is heavier on worlds, which is a really cool little fact. It's interesting to look at that each of these levels is about a factor of 1 billion to 100 billion larger. That's a coincidence. It's actually literally a coincidence because of some of the constants of nature. It actually doesn't mean much. But you could argue that, of course, since we tend to think in a logarithmic way, in some sense, actually going from an Earthbound civilization to a solar system civilization, that's almost halfway to the end of the universe as our thinking goes. And then, of course, there are questions what we should be doing with the universe. Maybe we should just convert all the matter into whatever material is happiest. Little servers running very blissful thoughts. And of course, it might be paperclips. Maybe paperclips is the goal. The interesting part is from an outside perspective, happiness and paperclips look almost the same. You have a civilization that races out and converts everything into something. But of course, it might also be that we want to think deep thought. We want to have grand civilizations doing complicated things and telling each other things, love letters sent over billions of light years, at which point we want to expand but still keep things together against the expansion of the universe. So we might go and take a supercluster, but then the rest of the universe, nah, leave that to the paperclip maximizers. But we are going to have our lovely supercluster together. And then, of course, we might just say, no, we're going to save those things. It's going to get cold eventually. In a few 100 trillion years, the stars go out, and then we can start working in our winter clothing in the kind of autumn of the universe. And so you save it and estimate until later. And of course, there are some people who think, no, we shouldn't. We shouldn't be doing all of this stuff. We should be staying at home. And the really interesting thing is probably we need to do moral traits between these views, because there are going to be some interesting arguments. I don't have the time to really talk about it, but I'm working a little bit with an astronomer by name of also actually looking at, if you look at super civilizations, if we actually see one, we can actually make some guesses at their utility function by looking at the way they're using energy and spreading. But basically, to sum up my argument, I think Kardashev was more or less right. There are some limits on communication because of light speed. And if we can do the right kind of automation, which we haven't demonstrated completely yet, but we're getting there, and if we can actually make the return on investment in solar collectors and stuff to actually grow, then it looks like we can expand indefinitely. At least if we get over certain thresholds. We know how to get into orbit. We haven't quite gotten to interplanetary settlement yet. We're a bit much further away from interstellar and the galactic one. If there is some limit on this expansion, it has to be something like an economic limit. There is some weird law of economics which means that eventually it becomes uneconomical to expand. Or it might be some weird complexity limit. It might be a coordination limit. There is some interesting issues about how long civilizations can last. Maybe they just build up too much complexity and then collapse. So that means plans cannot last longer than a civilization. However, that's a totally separate lecture. I have reasons to doubt that. We also have an interesting list of things that we would like to do, or at least demonstrate that we could. So I would love for my book, of course, to prove that we could do space mining, space manufacturing, and have children in space, but that might be a bit too much practical stuff for a book that's hopefully fully finished this year. But I think it's an interesting set of projects to actually work on. In order to demonstrate that we can actually make that social, we need to demonstrate that we can automate mining and manufacturing. For doing interstellar reach, we need really, really ridiculously reliable technology, which is another interesting thing anyway for users on Earth. And we need smart enough systems to do that, and probably nanotechnology. And for intergalactic reach, we need even more reliable technology, stuff that literally lasts for billions of years, which might be an interesting challenge. So I think the right column here might be a suggestion to you for problems to work on. Maybe not the entire column, but just one of them, or maybe a part of it. Because I do think many of the juiciest problems, you start with a grand problem, then you take some small part of that and try to solve it. That's typically when you get to the really interesting stuff. I don't have the time to really get into the coordination part, but there is a lot of cool things there. But generally, what I like to say is that it looks like the future is ridiculously, tremendously big. Potentially, they can literally be more than a Google future lives. Which of course means that we should get our act together now and not go extinct and miss all this glorious future. So we need to figure out a lot of coordination. And probably we need to actually think a little bit about a solidarity across time and space. I'm also having this agenda that I want to show that there is potentially a very positive future ahead of us. Because a lot of work we do at FHI is about avoiding risk. But avoidance, that's not really a good way of living. It's like you want to have an appetitive movement. You want to move towards something. You want to know, why should we survive? Well, because we could be so much more. Because we could live so long. We could create so much. We could change things. Yes, that is a tremendous responsibility. But it's so much more fun to know that we could get great responsibility and grow into that than just miss out on it. So I hope I whet your appetite for taking over the galaxy. Thank you. So, questions? Okay, let's start with you, and then you.
I actually have a question about this very last thing you mentioned, existential risks. So it seems to be possible that the space of all logically possible existential risks is enormous, and you're thinking about this particular subset really.
Yes
so,
and no.
What makes this subset special relative to all the logically possible sort of disasters that could happen?
Yeah, so there's some existential risks that are very fun because they're well defined and you don't need to worry about them. So there is, for example, one where all humans die of natural causes tomorrow. And we can calculate the probability of this, and it's ridiculously low, but it's a finite one. It's a real risk, and we can't really do anything about it. Another the absurd little risk is, of course, that all the air in the world moves away from human lungs. So you get a thermodynamic miracle, and we all die from it. And you can even compare the improbability of these two and see that, oh, one is way more probable than the other, but it's still kind of ridiculous. It's pretty clear that we should care much more about nuclear war and asteroids there. And even though we then know that asteroids are actually much less important than nuclear war. So in some cases you can put nice probabilities on it. In some cases the probabilities are weird, like the issue of artificial intelligence, because we, by thinking about it, might actually change the probabilities. So there is one deep philosophical question which I really like to get into, and that is, what's the principle, the limit where we should stop thinking about the weird risks? But there is also a really cool thing you can do. There are ways of bounding certain risks, so we can say this category of risk, which includes some we can actually name, but also an infinite amount of risk that we can't even think of, they all have a probability less than 1 in a billion. So the cool thing is, Nick Bostrom and Max Tegmark has one paper about mostly vacuum decay, but that actually covers a whole host of risks and can bounce that and shows that we can sleep well at night. We don't need to care about that. I'm working on a paper with Andrew Snyder-Beatty about risks to the biosphere, where we find another bound, which includes not just risks we can think of, but also unthinkable risks and things that no human will ever think of. And we can still show that, yep, and it's less than 1 billionth of a chance. So there are ways of dealing with this really weird space of risks. Of course, some people say, yeah, I'm just much more straightforward. I'm just going to deal with biorisks. I know my way around Ebola, and I'm going to try to deal with that kind of risk. So one should try to find the level that makes most sense to you. But there are ways of navigating this infinite space of crazy risks. So, you had a question.
Yeah, thank you so much for your talk, Anders. Would you be willing to share your mean probability estimates on the 4 futures that you described right now?
Yeah. So I think if we survive this century, we have a pretty good chance of getting a very big future. So I still think it's about 90% chance that we can survive this century. And I think if we do that, and depending on how you take that, of course you might say I'm very pessimistic or I'm very optimistic, but once we get our past there, I think it's fairly likely that we will at least settle the solar system. I would give that almost 75 to 80% chance. Settling the stars, well, again, maybe 75% chance of that, and settling the galaxy, again, 75% of that. Then, of course, how long we would last depends on a lot of very unknown factors. Especially, and it's interesting because I think these unknown factors are not so much factors about physics of the universe. Certainly the nature of dark matter, etc., does figure in what we can do. But the shape of our future is probably going to be dependent on cultural and even value-based questions much more. It might be that in 50 years' time some brilliant philosopher comes up with a really astonishing good argument for what we ought to do, and we all eventually converge on let's do that and let's implement this plan. That's going to have a way bigger effect actually than the nature of matter. But I can't say anything about that probability because, well, as Popper pointed out, you can't actually talk about future ideas, because if you actually knew that you would have that idea, you would already have it. It's not always true. We know, for example, that there is an idea for unifying quantum mechanics and gravity. We just don't know what kind of idea it is yet. But we know it should be out there somewhere, or that we're totally wrong about physics. But most of the time, we can't predict ideas. Yeah?
Can you mentioned briefly about there being a complexity limit. Can you explain a little bit more what
So, one of the simplest possible might be something like Joseph Tater's idea about the collapse of complex societies. So he made the argument that societies meet various challenges, they create institutions and systems that solve them, and eventually they become too costly. The return of increased complexity become too big, and it just gets top heavy, and it's much better to become a barbarian because you don't have to pay taxes and the society collapses. We might imagine something similar happening to other forms of complex organization. So we might imagine our post-human descendants forming group minds, and they distribute thoughts and have collective cognition, But again, this probably needs various forms of management, and now you need to streamline the information flow, and eventually the Borg collective gets top heavy and it might be rational to leave it. It could be that we have limits like that. I don't know how much I believe in that. I wouldn't exactly give it much of a probability, because in many cases I think we're using analogies to systems that we know well and assume that other systems must work like that. And that's not true. When you scale up some things, they become utterly different. A Stone Age tribe multiplied 1,000,000 times is not equivalent to a modern big city like London. London works really different from 1,000,000 Stone Age tribes. It's fundamentally different. That level of organization seems to allow London to do things that are entirely new. So if there is a complexity limit, it's probably going to be something really weird. And we don't really have good tools for thinking about complex systems. When I kind of grew up academically in the 90s, I was avidly reading everything the Santa Fe Institute of Complexity was publishing, and they were kind of groping towards a general theory of complex systems. It has something to do with kind of edge of chaos, etc., etc., and it never got anywhere. They got a lot of cool complexity measures, they found a lot of interesting systems, they learned a lot of things, but it never cohered into a nice universal theory of complexity. Maybe there isn't one. And so my complexity limit should be taken as hand-waving. But I think there's a very interesting question of saying, are there things in the soft sciences that are stronger limits than the light speed limits in the hard sciences? Because that might actually be really valuable to know. Yeah?
Should we be worried about superweapons with like cubic or exponential growth and stopping the sort of, even if we're growing at an exponential rate, that we might be stopped by sort of like a weapon?
I'm trying to do a calculation of that in the book actually. I got an appendix on the ultimate limits of the physics of war, which is such an epic title for an appendix. And basically, self-replicating systems, one interesting thing is that the time it takes for a replicator of mass m to replicate scales as the fourth root of m to the 1/4. So small things are much faster replicating than large things. So the kind of bacteria are more problematic than big killer machines. And for spreading over interstellar distances, however, you need fairly big ones. So the production rate is going to be somewhat limited. But still, there is this issue of what would we know, but I don't think we know. However, it's worth noticing that we seem to be surviving fairly well. We got immune systems, and they seem to be good enough to allow us to survive, even though there's a lot of pathogens out there trying to get us. Although they're not, strictly speaking, not trying to get us, they're just trying to replicate. It's the bioweapons that are actually out to get us, and we don't know whether our immune systems are out evolving those. But it's worth noticing that we spend about 20% of our metabolic energy on defending ourselves against pathogens. And if you look at the states, they spend at least a few percent of the budget, and in some cases up to 20%, on police, courts, laws, armies, against systems trying to prevent free riders and parasites and invasions. So it might be that many complex systems are going to be having this issue that they need to spend a fairly significant amount fending off other systems. So this might again be a complexity limit. Maybe beyond a certain size you get scaling, that means that it's hard to scale. However, there is a really interesting paper that some of my colleagues have worked on that actually argues the opposite. Once you scale things up enough, the defenders actually get an advantage. So it might be that if we get a sufficiently big civilization, everything gets really nice and peaceful. I don't know whether I truly believe that scaling argument works or not. I need to reread the paper a few times more. But it's a great question to work on. Yeah.
I was curious about a specific program. You mentioned the two Dyson spheres shooting at each other, and that's survivable by constant movement by them, or like how do you see that going?
So one mistake everybody in kind of bad science fiction does is thinking that a Dyson sphere is a solid shell. And anybody who's been studying mechanics at university level will know that, the net gravitational force on a shell is always zero. Haha, now I see why I can't build that. And it's also going to have a nasty buckling, etc. And Dyson, of course, being a good physicist, already in his paper suggested it's going to be free-floating solar collectors. Now, so, these solar collectors, if I shoot at your Dyson sphere, I'm going to vaporize a few solar collectors. But of course, you're going to notice who's shooting at you, so you might actually just tilt your solar collectors. So now my laser beams are just going to pass them by. And in fact, you actually have a lot of resource to build more solar collectors once I stopped shooting. So it seems like I'm able to destroy solar collectors at a fairly big rate, but I need to focus my star's energy on a small set of solar collectors to destroy them. I can't just beam all my solar energy at you, because then it's the same amount of light on both sides, and that's not going to fry anything. Because the solar collectors, of course, obviously need to be able to withstand the solar heat anyway. So I need to focus, but then I can only destroy a small area. And of course I can then move my laser beam around, but it might be unpredictable, and you might need to dodge, but it's very ineffective. The more I focus, the better I get to destroy stuff, but the fewer things I can destroy. And similarly, of course, if you try to retaliate, again, it can get in this silly slapstick fight, it seems. So it seems like if I really want to hurt you, I'm going to have to come up with something more devious in my super weapon arsenal. You over there, Nadir?
You kind of like I felt like you kind of glossed over the idea, the issue with like communication a little bit. So I mean, obviously there's like this fundamental limit with like the speed of light and stuff, but to what extent can you really call like an intergalactic civilization a civilization if you can never communicate with them?
Yeah, that's a great question, because right now we're in this weird situation that everybody is about 1/7 of a second away from everybody else, thanks to our modern electronics. Great, we're really integrated as a civilization, and that is kind of a unique moment in history right now. If we start moving out into the solar system, it's already going to mean that it's going to be at least 15 minutes before my search on the Martian internet is going to return the hits. That's going to be so annoying. It's going to be back to the early 90s again. I think most of you are too young to remember seeing the Netscape browser slowly load the images. But this is going to be even worse than that. And that's even within a solar system. Now, what really matters here is the lag between sending off a request and getting things back and the processing speed you have. So you could make an argument that if you have a really high processing speed, maybe you're a super advanced AI and you're running really fast, then you're not going to care about what's happening even the next city over, because that's so many light nanoseconds away. By the time you get an answer, you're going to have been thinking a million thoughts and completely forgotten what that was all about. So there are some people arguing that this is why we're not getting contacted by aliens. They're all running super fast in their own little computing clouds, and there is no point in talking to the rest of the universe. And I think this is a plausible answer, except of course that there are many processes that are happening much more slowly, where we actually do send off a letter and get a reply weeks later. Indeed, we have had civilizations that literally had months of travel time, and we needed to decentralize them. But I think we could still argue that the British Empire was an empire that was integrated, even though there was a lot of slowness. And even parts of a system might be thinking things at a very rapid pace, but be willing to wait for a long time. We see a lot of our own life projects. We might be thinking about our pension funds, using thoughts that are literally happening on a millisecond to second scale, but then making a plan that is supposed to happen over decades. So I think the relevant question is, the speed of local processing is not important, but the speed of change in how quickly parts of an empire or a civilization or whatever it is becomes something else. That might matter. So if by the time I get an answer from you, you have evolved into something completely different, so the answer actually doesn't apply, then we might not be able to communicate. This also, by the way, puts a limit on normal empires in the historical past. The natural size of an empire was so that the message that one of the provinces had rebelled, when it reached Caesar, and Caesar got there with a legion, the province didn't have a time to actually put together an army. If it was too large, of course, they could always defect. So you get a natural size. So cultural evolution probably actually sets the size limit of an empire. So it might be that if cultural evolution is just rapid and exponential, it might mean that we can't actually have a galactic civilization. But on the other hand, if things slow down, if we actually find the best way of living, or if everything is moving at a slow, stately pace, we might have a very big civilization. Yeah?
Anders, love the talk. The 80,000 hours career guide for non-software engineers currently recommends going into early stage 3D printing companies. It sounds like you've got quite a few other ideas what engineers could be doing. Could you maybe outline them?
Yeah. Well, 3D printing is really cool. The problem is throughput, or rather what you want to do. So if you think about Eric Drexler's original vision from the engines of creation in the 80s and later, that we use nanomachines to kind of 3D print stuff from atoms up. That vision has an interesting problem, but now you have a totally general tool for making general things, which is awesome. But it's also fairly inefficient compared to having a specialized tool for churning out a lot of things. So for making, let's say, keys for computer keyboards, it's not likely that any factory will ever have 3D printers making these keys, even though it's totally doable, of course. It's much better to have a plastic molding machine just making thousands and thousands and thousands of keys, but it can only make keys. But that's what it's needed. So it's very likely that we want to have the general 3D printers to make everything else. You want that as the kind of core in your industrial system. Just like right now in an industrial metalworking workshop, you have a lathe and some other tools that in principle allow you to make all the other tools. But for most purposes, you don't want the super general tools because they're less effective. You want the more specialized ones. And I think this is true also, not just in 3D printing, but in quite a lot of other domains. And generally, making general purpose technologies tend to change the rules quite a bit. That's why computers and the internet have been so powerful, because they're both general purpose technologies. But the things that actually people use is much more specialized. People use a word processor, people use a social medium of some kind. So that gets more specialized. I don't have a great idea right now for other engineering things, but give me some time to think about it, because I do think there is an awful lot of interesting stuff. As Eric likes to say, that's a manufacturing problem. An awful lot of what I've been talking about is basically just manufacturing problems. And I do think that many of the environmental and the material scarcity problems are good manufacturing problems that people can actually start tackling now. So there's, yeah, behind there, there's kind of two of you along a line here.
So you mentioned that some people nowadays prefer modest futures. And obviously, if we do survive and if we do go to space, the people who will go will be selected, right? Because they will be able and willing to go. So the people who will reproduce in space, if they do, will be a certain type of people. And then you will have evolutionary pressures that are new on them. So how likely is it that at some point you may separate, where you have the people who decided, like the conservatives who decided to stay on Earth, and then sort of new subspecies elsewhere?
Yeah, I think it's not implausible at all. Martin Rees, he likes to point out that, yeah, the crazy people are going to go to Mars and become transhumans and posthumans, and the sensible people stay at Earth. And maybe that's also a good approach. It's like America. Send off the religious people and the crazy people and the inventors over there and see what happens. The problem in bioethics that a lot of people have been discussing is, of course, maybe it's a really bad idea to allow humanity to split into different species. The question is, why is it a bad thing? So George Annas has been arguing that, well, inevitably it's going to be conflict. And that's painful and bad, and that's why it should be a crime against humanity to modify the human genome or trying to become a different species. That's slightly problematic, of course, because we all have a right to reproduce with whoever we want. And if we just decided in this room that we're going to start a new species tonight and so on to make sure that we are evolutionarily separate, it seems like George Annas would have a trouble getting the United Nations on us. But the real problem actually is, of course, do we form a collaborative framework, to use Alan Buchanan's term? the real threat is if you're totally separated, because then you might lack understanding. And most of the discussions in bioethics still deal with kind of people on Earth, maybe very genetically engineering or becoming cyborgs. And then the question is if there's enough overlap. Now the space case might be much more extreme, especially if people start adapting to space. After all, if you live in space, maybe you want to be able to handle vacuum and radioactivity much better. And now you might suddenly find the Earth's atmosphere rather stifling. And there's so little gamma radiation, so you can't see it and so on. So then you have a much more natural speciation and also slightly different needs, which might then diverge. Now, as long as the ecological niches are totally different, this might actually not be much of a problem. But really, I think there is a moral trade. Ideally, what I would like to see is one day you have kind of the leader of the conservatives shaking hand with the weird Martian transhuman, and they're agreeing that, okay, we get Earth and you get the rest. And they have a deal that can stick. Now, how to get that deal to stick is a really interesting question. My current best idea is blockchain, which is kind of feeling so last year by now. But basically, the idea would be that if you have some form of big economy, and you can actually put contracts into the economy. So breaking the contract means that you need to opt out of stuff that you actually care a lot about and is really important. Then you can actually probably make somewhat self-reinforcing contracts. I also want this to work because it's not just dividing space between the stay-at-homes who want a sensible, reasonable planet and the expansionists who want to do awesome and weird stuff out there, but also the people who want to come in late. People who want to survive for a very long time, and I'd like to sleep in because the universe is so hot right now, 3 Kelvin. I mean, you can't work at this temperature. They want the stars to go out, and then they can do the computations in a nice cold universe in a few trillion years. So they can leave things, of course, to the people who are kind of overly active right now. So they might want to make a deal that, yeah, we sleep in, but we get the universe in 100 trillion years when you're done with it. That contract also requires an economy that will last 100 trillion years, and this might be stretching blockchain. Even some of my friends who are absurd blockchain evangelists think that, whoa, that's ambitious, that maybe it's not something we can do, which is very rare to hear from somebody who's into blockchain. But this is my loose idea right now. But there is an important problem actually getting different moral views to fit. So far, we humans have not been great at it. But I think we've become much better over the past few centuries than we used to be. So the extrapolating in a few centuries, we might actually have a better idea how to do it. Yeah?
Yeah, kind of related to that, returning to the question of complexity and coordination limits. So this talk was obviously fairly technical, but you just recognized earlier in the Q&A that there could be great value in exploring some of the quote-unquote softer questions. Is there any ambition plan to do this within FHI? And if not, why not?
Sounds like an awesome research scholar project. Well, a lot of what we're doing in the macro strategy area, I think you could make an argument that's actually in the soft sciences. Although we might say, yeah, we're starting out from philosophy and then we'll try to see what fits in. So we have the AI governance people. They are, of course, mostly thinking about artificial intelligence, but we're using a lot of knowledge from economics, law, and political science. And I personally think, no, we need even more historians, and we need sociologists, and there is always room for more kinds of knowledge. In many ways, what I'm doing when I'm doing my hard tech stuff is dealing with the easy things, because physics is so well behaved. It doesn't care if you're observing it unless it's quantum. Otherwise, it's just going to be following its equations. Humans don't behave like that. Humans are complicated, reflective, and autonomous beings, and that makes it, of course, very interesting and very tricky to say anything sensible about it. But if you can find some general patterns, even if they're fairly weak and probabilistic, they're quite often much more important than the physical ones. So do I have time for
2 more questions?
2 more questions. Okay, so let's take your question and yeah.
Have you thought about the ethical issue of this desire for wanting to survive forever? It seems to be a natural part of evolution. But if say, for example, if your objective is to seek truth, then maybe AGI is a much better idea than humans. So have you thought about that?
Yeah. So if your goal is to personally survive, or say that you think your species should survive, many people don't care too much about their own personal survival, but are surprisingly interested in having a continuation, future generations. And you can do this both in a utilitarian framework, but even as a deontologist. In that case, you might say, yeah, maybe the AGI is way better at finding out the truth and surviving the universe, but that's not me, that's not my descendants. So they would say, yep, I'm going to try to make sure my descendants go. But similarly, some people might say, yeah, I want to find out the truth about the universe. I don't want somebody else to do it or an AGI to do it. While others would take the opposite view. Actually, the important thing is finding the truth, and then we can see what to do with it. So I think you can take different positions here. So when it comes to survival versus truth, that's totally different things. Survival is about playing this open-ended game about existing and trying to play that as long as possible. While truth might actually be closed. One day you figure it out. You got the answer to life, the universe, and everything, and now you're done. There might actually be mindsets and civilizations that are finite. They achieve what they want and then they kind of stop. And I think similarly you might have others that are constantly reinventing themselves, either that they actually want to survive or that they're actually finding new goals. There is quite a lot of different possibilities here, and it's not entirely clear that our current value theory has a good way of dealing with this. We can certainly look at the diversity among human views, and then most philosophers will typically like some views and not others and make arguments. These ones make more sense, but generally we don't have any consensus, and it's not obvious that we are approaching consensus. It's a really cool question actually. In 1 million years, will we all agree on ethics? What about 1 billion years? 1 trillion years? And depending on some of your meta-ethical views, you might actually be fairly assured. Immanuel Kant would say, of course, eventually people will be smart enough to realize I'm right. And then we will all converge to one ethical system. Well, the other views, of course, like Hume saying, no, we're just going to have different emotions and views, and we're never going to converge. It's going to be interesting to try to find out. So what I'm doing in the book is being very Scandinavian. Instead of taking too much of a side, I'm just trying to hash out what the different views would say and compare that to the different features and trying to see, oh, if these views are dominant, then we're going to try to do that. If those views are dominant, we're going to do that. And then trying to see what can physics tell us about it. Okay.
Yeah, so you said earlier that this sort of investigation would kind of affect what happens in a day or a week, or the decisions we make in like a year, and that would all kind of play out. I was just wondering kind of if you could expand on that, and if like, you know, if 100,000 researchers were working on this and you made loads of progress on all these questions about what's going to happen in a million years, like how would it affect the next couple of decades?
So I think one of the important things is obviously existential risk reduction. That seems to be a no-brainer. Except that there is some other interesting things. So X risk might actually be joined by S risk. Suffering risks might also matter. So I remember when Kai Sotala presented suffering risk to us in Gothenburg 2 years ago now. And we started thinking, maybe there's a whole alphabet. Maybe there's Y risk and Z risk and A risk and risk we haven't even, there might be things that need to be discovered. But certainly we know there are things like suffering that are bad and extinction that are bad, and those we want to reduce. There is also this coordination thing, because as that conversation implied, once we start spreading out too far, it's going to be very hard to coordinate. And if we need to coordinate about certain things, and I think there is actually a fairly long list of things we might want to coordinate about, we need to get together to do that. And as Will MacAskill suggested, maybe we need a long reflection, which might actually be really long, maybe 10,000 years, where we actually decide what we're going to use the universe for. Because if it really is sensitive to coordination issues, and if we can really flub it up, if we make self-replicating killer systems or whatever, then we might actually want to really get our act together very strongly. That view seems to imply that we should be thinking about how can we actually improve the coordination ability of the world, because obviously we can't do the long reflection now. But we're certainly better able at coordinating now, even with the United Nations and all its limitations. That's amazingly much better than how it was a century before the United Nations. Because in that era it was unthinkable for most of the world that you could even get all the nations of the world together in one place to talk about everything, let alone make a few binding resolutions. So in 100 years later, we might be able to do even better. So we might want to try to figure out how to move in that direction and figure out to make the tools, to make the tools, to make the tools to make a grand future. Thanks.